CS408, Linear Algebra Concepts and Notations. This material corresponds to Appendix D in the Cheney and Kincaid text on numerical analysis, and it provides a quick overview of basic concepts in linear algebra. While linear algebra is required for 407, not everyone may have taken that course due to CS408 being offered as a special summer offering. Even if you have taken the course, it's always good to have a refresher on some of the concepts. The material for this presentation can be found in Appendix D of the Cheney and Kincaid textbook. If you're in need of some very basic background, there are a lot of pre-calculus texts that also cover these concepts and cover them in a nice, smooth, introductory way, and shouldn't be too challenging for you to read. So, if you'd like to take that approach, that would work as well. So, two critical concepts that we're going to have here are vectors and matrices. And these two concepts from linear algebra are useful in compressing complicated expressions into a compact notation. So here vectors and matrices are most often real numbers, but these concepts can extend to complex vectors and matrices. So we can start out with a vector as a member of the real numbers raised to the n can be thought of as a one-dimensional array of numbers written as x is equal to x1, x2, all the way down to xn. And this should be familiar to you from the C++ concept of vector or array. An alternative notation that's useful in the pseudocode in the text is x is equal to x sub I sub n. Sometimes the vector x displayed above is said to be a column vector to distinguish it from a row vector. We can write column vectors in the same way using the transpose symbol that we'll get to in a while, but basically transpose just means interchange the rows and columns. So many operations involving vectors are component by component operations. For example, if we want to compare two vectors for equality mathematically, x is equal to y if and only if x sub I is equal to y sub I for all I. So if all the components are equal to one another, the two vectors are equal. Same thing for less than and greater than. Addition works by adding each component, and scalar multiplication involves multiplying each component by a scalar value. A special set of vectors that stand out are the standard unit vectors. And here, basically, E1 is 1 in the first position, 0 elsewhere, E2, 1 in the second position, and 0 is elsewhere. En is assuming that it's a 1 by n vector, the 1 is in the last position. And we can use the linear combination of these to get particular vectors from these where alpha here is a scalar. So any vector can be written as a linear combination of the standard unit vectors along with particular scalars. And we can get those to express matrices in that way, or vectors in that way. We can also consider the dot product or the inner product of two vectors, and this should be familiar with you too from matrix multiplication, which we'll get to in a few minutes. Basically, x1, x2 out to xn times y1, y2 down to yn is equal to the sum of the xi times yi component. So x1 times y1 plus x2 times y2 plus dot 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 plus x sub n times y sub n. So moving along to matrices. A matrix is just a two-dimensional array of numbers that can be written in a rectangular format, where Aij is called the element of entry in the ith row and the jth column. The entries in A can be grouped into column or row vectors if we so desire. And a column vector is also an n by 1 matrix, and a row vector is a 1 by n matrix if you're interested in classifying the vectors in that manner. An important matrix is the identity matrix, and basically this one just has ones on the diagonal. And so it's composed of those individual unit vectors. A matrix of the same general form with different values on the diagonal is called a diagonal matrix. And we can also use blank space to indicate zeros if we so desire. These are Useful because we can save space in representing them in the computer. Rather than a two-dimensional array within squared entries, we just need a one-dimensional array within entries in order to represent these, even though they're two-dimensional structures. The tridiagonal matrix is a square matrix of this form where the diagonal entries a sub I, d sub I, and c sub I are called the subdiagonal for the a sub i's because they're below the diagonal, the main diagonal, which are the d's, and the superdiagonal, which are the c's because they're above the diagonal. We can also have efficient storage for these matrices. Basically only need 3n minus 2 storage spaces, and we have specialized systems for solving them more rapidly. So if you have something in this form, it's good to recognize that it's in this form or any type of banded form because they can be more readily solved. Other forms, it's a diagonal matrix if a sub ij is equal to 0 when I is not equal to j. It's a tridiagonal if a sub ij is equal to 0 whenever I minus j is greater than or equal to 2. Lower triangular matrices basically have everything from the diagonal down having values and everything from the diagonal up having zeros. And an upper triangular matrix is one that just has the zeros below the main diagonal. And so pictured here are the identity, diagonal, tridiagonal, lower triangular, and upper triangular. All of these have efficient storage forms and solution strategies that can assist us in solving things. As with vectors, many operations involving matrices correspond to component operations. So two matrices, A and B, are equal to one another if and only if all their individual entries are equal to one another. A is less than or equal or less than B if and only if all the elements of A are less than or equal to their corresponding elements in B. Additional scalar products are defined in the following ways. Basically, it's a component-wise addition. And assuming A is a constant here, we just multiply each entry in A by that constant. A matrix multiplication, you're likely going to remember this process intuitively rather than by the formal definition I presented here. A bit more informally, we let A be an m by k matrix and let B be a k by m matrix. So those two k's have to match up in order to multiply them. The product of A and B is denoted by AB and is the m by n matrix with the ijth entry equal to the sum of the products of the corresponding elements from the ith row of J and from the ith row of A and the jth column of B. Matrix multiplication in general is not commutative. It may happen that A times B is equal to B times A, but that's not always going to be the case for any general matrix. There are algorithms for matrix multiplication. The basic algorithm is going to require some bit of work on the computer's part and probably on the programmer's part as well. There are basically n cubed multiplications and n squared times n minus 1 additions, so it's O of n cubed. More efficient algorithms exist that are on the order of O of n raised to the square root of 7 that have been developed. You're probably familiar with the column-wise way of multiplying matrices. So here we would take 3 times minus 1, 1 times minus 3, and 7 plus 7 times 2, and we would get the first result there. So we get minus 3 plus 1 minus 21. That would give us minus 20 minus 23, and then we would do the same thing for the second row and the first column. Same thing for the third row in A and the first column in B. And then we can compose C1, C2, and C3 together. So that's the column-wise way. You can also do this in a row-wise manner if you're interested in doing that. The transpose of a matrix, transpose basically is obtained by interchanging the rows and the columns, as you can see here. Now, if it happens that A is equal to A transpose, then the matrix is said to be symmetric. Some useful properties for matrices, as we mentioned, A times B is not necessarily equal to B times A in general. There are cases where that happens. An example is in the second point with the identity matrix. A times the identity is equal to I times A, which is equal to A. The zero matrix is also commutative. Transposing the transpose of a matrix gets the original transpose. Adding two matrices, then transposing them is the same as transposing each one and then adding them together. And multiplication of the transpose of the product is equal to of AB is equal to B transpose times A transpose. If A and B are square matrices that satisfy A times B is equal to B times A is equal to I, then B is said to be the inverse of A, which is denoted as A inverse. Also, so A times A inverse is equal to A inverse times A, which is equal to the identity matrix. So sometimes multiplication can be commutative, but not always. As a final set of examples, we have the product of matrix times a vector and of two matrices. So you can see what the product would look like in this, with the x1, x2, x3 vector puts this in the nice form of some simultaneous linear equations. And the lower one is actually going to be useful in matrix factorization, which will give us the LU matrix factorization form that we discuss in chapter 8.1. So we'll see that in the next presentation. And finally, we get to Cramer's rule, which tells us the solution of a 2x2 linear system of the form ACBD times XY is equal to FG. It gives us the solutions for X and Y in terms of the determinant of different matrices. The setup is FCGD and the AFBG, and so we can actually get the solution to that in a special case, and that's Cramer's rule. As an example, you can take minus 1, 1, 2, 1, xy is equal to 1, 4. D is equal to the determinant of minus 1, 1, 2, 1, which is minus 1 times 1 minus 2 times 1, which is equal to minus 3. So x is equal to minus 1 third times the determinant of 1, 1, 4, 1. Which gives us 1, and y is equal to minus 1 third times the determinant of minus 1, 2, 4, and that gives us 2. So we can find solutions for x and y. So Cramer's rule is a handy little tool for these small matrices. Thanks.